It's a great pleasure to welcome you to this ILL ESRF colloquium, which is a special one because since 2.5 years, it's the first time which will be held in hybrid, which means with some local attendance also. And it's a particular pleasure to welcome Don Brown from Los Alamos National Lab. So he is in the Material Science Division, and more specifically, he works as a instrument responsible of a smart spectrometer, which is a kind of salsa for engineering applications, but with time of flight. But he's not only focused on neutron studies of materials, but complements this with studies with X-ray diffraction at the advanced photon source. And he applies this for a large variety of fields, where he will tell us a shortcut cross-section of his activities today. So please, Don.
Thank you. Everyone, thank you for the chance to be here. I'm really excited. It's been a long time since I've been to the ILL and the ESRF. I first came here, I think, before the ESRF was a hole in the ground, in about 1994 or 95, as a graduate student doing inelastic scattering. Today I'm going to talk about diffraction measurements and imaging measurements under simulated manufacturing conditions. I'll focus a lot on additive manufacturing because that's very much the buzzword around the literature nowadays, but quite frankly, Los Alamos is interested in all forms of manufacturing, advanced manufacturing to be more generic, whether it's casting, welding, forging, machining. Those are all things that are at least as important to us as additive manufacture, but additive manufacture hits a certain audience nowadays, so I will focus on that. This work is done, of course, with a lot of help. John Carpenter is our, maybe we could turn down the lights a little. John Carpenter is our leader from the real materials point of view. He's the guy that understands all the engineering. Björn is my co-instrument scientist on SMARTS. Jason Cooley is the one that develops the sample environment for in-situ additive manufacture. And then just a lot of collaborators. Maria Stronza was a postdoc. Darren Pagan's the instrument scientist at Chess. Junsun Park and Peter Kennessy, a lot of people in this audience might recognize, are instrument scientists at the Advanced Photon Source. Okay, that was my talk. There we go. Okay, so I'm going to talk a little bit about LANL's mission, because while we have a Neutron source that is a user program, we are very much focused on the mission at Los Alamos National Lab, which is a bit distinct, and it makes our user program different than your average user program, or for that matter, any other user program that I know. First and foremost, our mission at Los Alamos is stockpile stewardship and maintaining the nuclear deterrence, which of course, over the last 3 or 4 months has become much more in the public eye and has resulted in us doing quite well in terms of budget. But you can imagine our mission, and I've kind of tweaked this a little bit to make it kind of European. You can imagine keeping an F1 race car in tip-top shape without ever being allowed to test drive it. And this might be a 60-year-old, in this case, F1 race car, and the first time you turn the key, it has to start, and it has to work at tip-top shape. And this isn't a Ford Pinto. There's not a lot of design error. This is designed right to the margins, and it's going to sit in the garage for 60 years, and every year you have to tell the people that count on that car that when you turn the key, it's going to work. That's our mission at Los Alamos. Every year our director signs a paper to the President of the United States saying that if you turn the key, this race car is going to work. That's what we do. We have some other things that we are part of, protecting against nuclear threats and similar emerging threats and opportunities. Certainly additive manufacture roles in here. This is worrying about what our adversaries might be doing. And energy security. Certainly over the last decade or so, it's become more in vogue to think of energy as a security concern, not just a economic concern as well. Materials, of course, material science plays a role in all of these things. It pervades all of the LANL mission, so it's very important. It's one of the pillars of Los Alamos National Laboratory. And of course, additive manufacture is a very popular part of that, and the things that make additive manufacture so relevant to Los Alamos, it's a little different than what might make it relevant to Boeing, for instance. But the idea that you know, AM is very well suited for small lot production. If you want to build one of a widget, then additive manufacture really makes sense. If you're going to build 200,000 of them, then additive usually isn't the way to do it. But if you're going to build a handful, additive is very beneficial for that. It can increase responsiveness and agility. So if you want to change a widget from one design to a slightly different one, you can do that quite quickly. It enables reduction of waste. The buy-to-fly ratio is much smaller, right? You know, if you think about making airplane parts out of titanium, quite often you might use 15 kilograms or more of bare titanium to make a 1 kilogram part. Well, when your materials are very expensive, which a lot of our materials are very expensive, you don't want to accept that buy-to-fly ratio, and often additive gives you a way to reduce that. It gives you a reduced manufacturing footprint. So instead of having to cast a metal, roll the metal, forge it, machine it, all those things take space. Maybe you just have an additive manufacturing machine that takes up a corner of a room. And finally, it can add functionality to components. And in my mind, this is where additive really has something to offer. If you can make a component that could do something that it couldn't through conventional manufacturing, then you're really gaining something. I find that lots of time additive gives us these nice ideas and we get all interested, but until you can really add a new functionality, it never quite, most of the time it doesn't quite make it from an economical alone point of view. You have to really add functionality. So of course, additive manufacture results in different microstructures and different properties, because microstructure, of course, controls properties. You have lots of problems with residual stress in additive manufacture. You can get cracks, fractures as you're building the part. They can happen after the part is completed. But maybe less obvious, it also often results in materials properties that are fundamentally different than conventionally manufactured components. This is a comparison of additive Ti6-4 to standard wrought material, which is the dashed line. You see that in every case, and it varies depending on how you do it, but in every case, the additive Ti6-4 has a higher yield strength, higher flow strength, and less ductility. That's because the microstructure of additively manufactured Ti6-4 is different. So that's just the nature of the beast with additive. It's going to create microstructures that are different than we're used to. Almost all of the alloys that we use were designed for casting. That means they were designed to cool down slowly. Ti6-4 is a great example. When you use additive manufacture, it cools down at 1,000,000 degrees per second, and the vanadium doesn't have time to move around where it wants to be. So you end up with a very metastable microstructure because you've frozen the vanadium into a phase it doesn't want to be in. That gives it different properties, but it also means it might not age well, because as it sits at temperature, then that vanadium might move around. So additive offers some unique challenges. And that's where my team really fits in, because what my team can do is really measure microstructure. And microstructure is the linkage between properties and processing. And I shamelessly steal this analogy from Rusty Gray. If anybody knows Rusty, please don't tell him I use this. He gets a little angry at me. But I saw him give this analogy once, and I think it really fits. If you think about potato chips, right? You have, your good old-fashioned Ruffles. Recently, you've come out with Kettle Cook, right? That's kind of a modern thing, and Pringles have been around a long time. The ingredients of all these things are the same thing, right? Potatoes, salt, oil, more or less the same thing. The properties, however, are quite different. The taste, the crispiness, the texture are all different. Those are all controlled by the processing that come about to make each of those three different products. Well, the in-between step in those, the processing controls the microstructure, and it's the microstructure that dictates the properties of the material. And the same is exactly true of 304L stainless steel. All 304L stainless steel has a certain amount of chrome, a certain amount of nickel, a certain amount of other things, but how you make it dictates the properties because you control the microstructure. Here is that example in terms of metals. So beryllium is a material that we're interested in at Los Alamos. You can imagine as an analog, magnesium or zirconium behave very similarly. But here's a microstructure that is hot pressed powder beryllium. And here's the same microstructure after rolling. Okay, the grain structure is obviously very different. The alignment of the crystals are very different. The amount of dislocations in the material is very different. So it shouldn't be surprising to you if you look at the properties. And here is the stress strain curve of the wrought material at different strain rates, and the stress strain curve of the, this is the hot pressed, this is the wrought material. The macroscopic properties of those two are very different. The flow strength is very different. The worked material is much stronger. That's the properties that link, that's the microstructure that links the processing to the properties. My team sits squarely on the materials tetrahedron. Being in the material science and technology division, I'm contractually obligated to show the materials tetrahedron anytime I give a talk, so I can check that box now. My team sits squarely on the structure corner of the materials tetrahedron. We use diffraction in order to, as a window into the microstructure of the property. We use neutrons and or high energy X-rays because they give us a window into the inside, into the bulk of the microstructure. Both will penetrate materials to macroscopic distances, and that's what's valuable. We will collect diffraction and we'll pull certain parameters out of the diffraction pattern, things like the peak intensity, the peak position, which tells us how far the atoms are away, and the peak width, which might tell us about heterogeneities. Now, the real trick, and I'll go into a good bit of detail about this, is how you separate all the microstructural features that contribute to, for instance, the interatomic spacing. Once we have that structure, then we want to relate it to the actual quantitative microstructural parameters. And this is a very important point to me. If you're going to walk out of my talk with one point today, this is it. At Los Alamos, it's extremely valuable that we come out with quantitative microstructural features. We need to come out with a dislocation density, not a peak width. We need to come out with a phase fraction, not a peak intensity. When I was preparing this talk, I was a little concerned that maybe this was a little bit obsolete and maybe this wasn't necessary. Just last week, I was at the ICSMA conference, International Conference on Strength Materials, and I saw a researcher that I really respect show some data from in-situ additive manufacture. And they're showing the 2 theta of a peak, and the 2 theta is getting bigger. And she says, well, this is the temperature cooling down. And then the 2 theta turned around and went the other way. And she said, well, this is residual stress, with no attempt to quantify it. And that's perfectly valid. And the reason she did that is because she's trying to go really fast. She wants to get data as fast as possible. But that's not helpful at Los Alamos. At Los Alamos, I need to know this is what the phase fraction is doing, right? This is the value of the residual stress, not, oh, look, there is a residual stress. So in the measurements I'm going to show you, we make sacrifices in terms of speed so that we can get quantitative microstructural information, and you'll see that. In my mind, that means we're not quite ready. Maybe the ESRF is now, maybe detectors aren't, but we're not quite ready to look at in-situ powder bed fusion other than in certain ways, because the detectors aren't ready to collect the quantitative data at the rate we need. And I'll show you examples of that, where we tried to really push the limits. And I will state that the measurements I'm going to show you were done about 5 years ago. So the limits are now a lot different than they were then, but the lesson is still the same, that at least, again, for our purposes, we have to make sacrifices in order to get quantitative information. So if we look at what's contained in a diffraction pattern, so for this interatomic spacing, which you get from the position of the lattice parameter, or the position of the peaks, there are at least 3 things that are relevant to material science included in that peak position. Temperature, of course, affects the interatomic spacing. Stress affects the interatomic spacing, and you have to break stress down even further. There's macroscopic stress fields, which are usually referred to as type 1. And there are intergranular stress fields, which are usually referred to as type 2. Both of those will affect the lattice parameter. And finally, one we don't always think about, but we should, is solute chemistry, right? If you're looking at Ti 6.4, where the vanadium is in Ti 6.4 affects what the lattice parameter is. And that affect's actually large. It's much larger than you'll get from stress. It's about the same as temperature. So all of those things are convoluted into your measurement of lattice parameter. And if you're in here, where all of them are varying, they can be very difficult to convolute, and I'll go through how we try to do that. And I've actually drawn this very much not in reality. It's not just a small area where these 3 intersect. It's actually almost the entire area of measurements that you're going to do have some intersection of these different microstructural features that all contribute to the lattice parameter. And the trick, in my mind, is being able to pull out, again, quantitative microstructural features despite that intersection of these. If you go to peak intensity, you have the same problem. You have phase fraction, you have texture, and you have the Debye-Waller factor. If you're up close to the melting point. At room temperature, the Debye-Waller factor is usually not a problem, but if you're at, say, 80% of the melting point, it becomes relevant. All of those things affect the peak position, and if you don't do enough measurements with enough quality, you can't separate them. And don't even start about peak width, right? The things that contribute to peak width are just an endless list. So deconvoluting all these effects are a lot of what I'll talk about. So just an example, how do we deconvolute the lattice spacing, for instance, all the microstructural effects on lattice parameter? Well, if we look at just a schematic of a Debye shear cone, that's supposed to be a circle, right? If we have a stress-free powder or a stress-free sample, then a Debye shear cone will be a nice circle. If we change temperature, for instance, temperature is a scalar, and maybe I should say this should focus on cubic materials where you have just a single thermal expansion. It's a little more complicated in hexagonals because your thermal expansion is direction dependent. But if you just change the temperature or the chemistry, those are scalar values. They're going to change the radius of your Debye shear cone, but that's all, okay? If you put a stress on it, you change the shape of the Debye shear cone. You turn it into an ellipse. So if I pull on it, the direction that I pull on it actually gets smaller 2 theta, because as d space gets big, of course, it's an inverse relationship. So theoretically, I can separate those 2 effects because one changes the radius and one changes the shape. And finally, if my stress isn't uniaxial, if I have a shear, then that ellipse actually rotates. Okay, so I can separate those 3 effects because if I measure the full ring, then I can separate what's temperature from stress and shear in this case. Now I need to do that measurement with sufficient accuracy. Typically for mechanical strains, we want an accuracy of about 100 parts per million. That's doable with today's detectors. In order to get the full ring, you have to have a very big detector, at least with X-rays. With neutrons, it's a different thing. So you need a big detector, but you need good enough resolution to get the lattice parameter. In order to separate the intergranular stresses from the macro stresses, you have to look at multiple rings. So your detector has to be big enough to, say, catch 5 full rings. That's kind of what's usually in my head when I design an experiment. Usually to separate temperature and chemistry, which both just change the radius of the ring, you have to have some extra knowledge. For instance, I can have a thermocouple on my sample, and that'll tell me the temperature. Or quite often what I like to do, because I don't trust thermocouples because they're often removed from your sample a little bit, I like to put the sample, say, in a can of something else. Like if I'm measuring titanium, I put it in a steel can, and then I measure the lattice parameter to the can, and that tells me the temperature of the can. And I get that measurement for free. So if I have an extra piece of knowledge, then I can separate temperature from chemistry. All these issues come when you're talking about trying to separate texture, phase, and the Debye-Waller factor as well. Very similar set of problems. Now, one thing I haven't touched on here, both stress and texture are very much 3-dimensional problems. If you're trying to do a dynamic measurement with X-rays, or neutrons for that matter, of texture or stress, you only get one 2D measurement, right? You measure the whole cone, but that's only a 2-dimensional measurement. You can't get stress without assumptions, without having more measurements. And if you're trying to go very fast, you don't have time to rotate your sample, or if your sample is in an additive manufacturing rig, you might not have time or the ability to rotate your sample, which makes getting stress and texture another step harder because you inherently need a 3-dimensional measurement unless you can make some symmetry arguments, and I will do that as we move on. So that's all the background, and that's, I can sort of step down from my pulpit if this is how I believe my measurement philosophy is. So a little bit of background about me. I sit at the Los Alamos Neutron Science Center, LANCE, in Los Alamos. So LANCE consists of a proton accelerator, which is, 2/3 of a mile long. It accelerates protons to 800 MeVs. Part of those protons we use for proton imaging, just like X-ray imaging, but with protons, or neutron imaging for that matter. So that's the accelerator. At the very beginning, we make isotopes, which is very much not our mission at Los Alamos, but we do make medical isotopes, so we get a lot of credit for it. There are only 2 places in the United States that can make Moly-99, for instance, which is used in some sort of cancer scan treatment. Brookhaven makes them. They can make them 6 months out of the year. We make them the other 6 months out of the year. The medicine only has like a 7-day half-life. So it's pretty important that one be active at each time. We have proton radiography I had mentioned there. The Neutron Scattering Center, that's where I sit. And finally, Weapons Neutron Research Facility, which is something distinct. It uses the unmoderated neutron source for various reasons. I'm not going to go into that. So that's the neutron source, but neutrons aren't always the right answer, which is why you have the ESRF built next to the ILL. Even though we have our own neutron source, we still use the X-ray source when it's the right tool. That's another big proponent of mine, is use the right tool. You know, don't use neutrons to study vanadium, for instance. So advanced photon source, you guys are all very familiar with that. When we need to use that, when we need to be fast, we go to the advanced photon source or CHESS, or hopefully in the near future, ESRF. I know my team would be very happy to travel to Grenoble. Now, I certainly don't want to get into you know, who's better, neutrons or X-rays. You folks know that as well or better than I do. I will go through some of the valid points that matter, though. Neutrons, that's a picture of my instrument, SMARTS. So I list here best spatial resolution of 0.5 millimeter. It's true that I can do a measurement with 0.5 millimeter resolution. It takes me 6 hours to get one diffraction pattern. That's actually something I can do now that I'm mission focused. I'm not paper focused. That allows me the leeway to do that. But in reality, almost 90% of the time, our best resolution is 2 millimeters, not a 0.5 millimeter. Count times can be 5 minutes to 60 minutes. We can move big parts around, so we've done 1,000 kilogram parts, 1,500 kilograms are capacity. I still would argue that for bulk 3D measurements in large parts, neutrons are still the way to go because some of the details of X-rays. But titanium and vanadium are very difficult or nearly impossible because of the coherence cross-section of the two. Don't need to go into details. X-rays. In the US, APS and CHESS are the only games in town for high energy X-ray. To me, high energy X-ray means 65 keV or more. Sub-millimeter spatial resolution, way sub-millimeter. I get it. Sub-millimeter is actually underselling it. Count times, milliseconds to minutes. And again, I know milliseconds is also underselling it. I know you can go to less than milliseconds. It's best for small samples. I don't think there's much argument there, and especially for 2D samples. If you have, I was talking with somebody before the talk about the convert fuels for the program to convert high enriched uranium to low enriched uranium in research reactors. Those are essentially two-dimensional foils of uranium molybdenum in those. The X-ray beam is really great for measuring stress in that because you can make assumptions about the out-of-plane stress field. That's where the synchrotron beam, in my mind, really shines for stress measurements. But as you crank up the energy, you can start to go through quite thick parts and get three-dimensional stress fields, even in thick parts. Titanium, you can go through 2 centimeters. Iron, 5 millimeters, probably a bit further than that. And for the things that I care about, even uranium, and we've now even demonstrated plutonium, you can go through 0.5 millimeter of material with 100 keV X-rays and get bulk information in a way that you couldn't 10 or 15 years ago. I wasn't expecting sound. So this is my first example. We're doing an in-situ additive manufacture. Again, because, well, first of all, this was in 2017, so the detector was slower. So we did wire arc additive manufacture because we knew the kinetics would be slower. Going into it, we know this is cooling at something like 1,000 degrees per second, not 1,000,000 degrees per second like powder bed fusion. Okay, so again, we sort of tried to pick a problem that would fit the kinetics of the measurement, which in 2017 at the Advanced Photon Source dictated doing wire arc additive manufacture rather than powder bed fusion. It's actually what's called a cold metal transfer machine, which is basically a MIG, but a little bit better control of the process, which means doing science is a little bit better. The measurements were done at 1ID with about 72 keVs of X-rays. The beam size ranged from 50 microns to 200 microns, depending on what we were trying to do. And our best time resolution was about 1/10 of a second. That's fully set by the detector in 2 parts. It's 1, the fastest the detector can read out, and 2, because the material is somewhat grainy and we tend to saturate individual pixels. So this was not at all set by the flux at the APS. In fact, we had something like a 10 times reduction in the beam to prevent the pixels from saturating. So this was fully set by the GE detectors that they use at the APS. I understand, Eiger's now running at 500 hertz could do this measurement at that rate. So I wasn't able to get the movie on here, but this was part of a movie that shows the deposition of, this is what we call a point deposition. You can't quite see the wire coming down here, but this is just a little ball of material. Here you can see a cold ball over here. that's being deposited. This ball will be about 3 millimeters when it's done. And what we're doing is passing X-rays through this little ball of material and collecting the diffraction data on the other side as we're doing it in order to get to that microstructural information as I was talking about while the microstructure is actually forming. We've gone through most of this. So when you collect the data, this is what the 2D diffraction image looks like on the GE detectors at 1ID. You guys have seen lots of stuff that looks like this. We analyze the data in two different ways, again, because we're going to try to deconvolute the effect of temperature from stress. Now we're lucky, this is, I don't think I said it, the material was 316L stainless steel. I'm sorry, that's wrong. It was 308 stainless steel, which is what you tend to use to weld 304, because it has higher chrome. Sorry, you didn't need to know that. Where we're lucky is that the majority elemental materials in stainless steel, iron, nickel, and cobalt, iron, nickel, and chrome, all have very close to the same metallic radius. So we will see that the chemistry does change in this, but it doesn't affect the lattice parameter very much. So this is one of those pieces of external knowledge that allows me to exclude chemistry evolution when I try to separate temperature from stress. And I'll separate that temperature and stress first by finding the radius of the rings, which is what's related to temperature, and then the ellipticity of the rings, which is what's related to stress. So I'm going to pass through this because I have way more to talk about, and I've already talked about this a little bit. This is just making the point that you really can't get a stress from a two-dimensional measurement. When you do a 2D measurement, you can only get one corner of the strain tensor. You can't get any information about the three direction. If you want to calculate a stress, you have to make assumptions about symmetry or about free surfaces, things like that. Sometimes those assumptions are valid, sometimes they're not. I'm not going to go into the details of that. So here's what the results look like. This is just an image of what one of these point depositions looks like. And what we did is we deposited these with the beam in 3 different places, 3 different little balls that we made. But we put the beam at 3 different heights so we could get the kinetics of the microstructure formation at these different positions. So one of the first things you might want to pull out are the phase fraction. So stainless steel solidifies. If you're doing it right, it starts off in ferrite and then transforms to austenite. We get it kind of partially along the process. We never see liquid in these, by the way. We're not fast enough to see the liquid material. We get it when it's about 60 or 70% austenite, and then it, quite quickly, here are my units of seconds, right? So within one measurement point or two, these measurement points are separated by 1/10 of a second, we're up to pretty much fully formed austenite, where you would expect it to be about 95% of the volume fraction. You'd expect a residual ferrite of about 5% in this material. So we can, in some sense, measure that solid-solid phase transformation, but clearly we don't have enough resolution and time resolution to really say we've monitored the solid-solid phase transformation, and we've completely missed the liquid to solid phase transformation. Here's where we pull out the temperature. So this is showing the lattice parameter as you go around the ring of the Debye-Scherrer cone. So that's what 0 and 90 are referring to here. These are the lattice parameter along the different directions. 0 is parallel to the substrate, 90 is transverse to it. You'll see it comes down and you see a significant separation down here. So this is temperature. Going from here to here is the effective temperature. That's 1400 C is about what you go to from molten steel to room temperature. This little spread right here, that's stress. If you blow that up, you can see again, that's not noise, it's not uncertainty. That's from the stress in the material. You'll see along the 0 direction, which is parallel to the surface red, the lattice parameter is bigger than you'd expect it to be. That's because the cooling material is trying to shrink, and the cold material underneath it is constraining it, not letting it shrink. So the lattice parameter parallel to the surface is too big. The Poisson's ratio gives you a lattice parameter transverse to the surface that's too small. If you average them all out, you get sort of what the temperature is doing. So that, again, is how we separate temperature from stress. So we can pull out the temperature as a function of time. So you can see it drops. These lines here kind of bound the melting temperature of 308 stainless steel, depending on the exact chemistry. So it actually forms right about where we'd expect it. This is, again, the solidification temperature. Cools very quickly. We can pull out the cooling rate At the maximum, it's at about 1,000 degrees C per second, which is what you expect. So we get reasonable definition of the temperature profile, especially once it's in the austenite and you're cooling. Or, I'm sorry, once the welder's off and you're cooling, but not great, right? The time resolution of this just isn't great. At this time, there really weren't any other options for higher time resolution, at least not at the advanced photon source. Oh, I forgot to show, this shows the stress evolution. So the waviness of this, that's the ellipticity of the Debye-Shearer cone. So it starts out, this is at late time. So this is after it's cold. Sorry, I should point here. So this is after it's cold. This sinusoidal curve is the residual stress in the material. This is what it looked like when it first started. So this was the first measurement as a solid, and you see now that sinusoidal curve is gone. That's because it's hot and it's soft. It really can't hold a stress. As you progress on in time, you'll see that sinusoidal curve develop, and you see it both change in magnitude, and you'll also see it change in position. That's the shear strain evolving with time. Okay, so we can watch the evolution of that, and we can plot it. And again, we're really not getting enough time resolution. You know, here we are at maximum temperature where everything's zero. We get maybe one data point where the stress is growing, and then we're pretty much, not quite, but almost constant the rest of the way out. So again, not the point of this measurement, one of the points of this measurement was to push the technique to its limits. And this is really where we're finding it. We didn't have quite enough time resolution. And as I started to say earlier, we didn't have any way to measure faster. So the next idea is, how do you slow down the process? So instead of putting down just a point deposition, we would put down a line of material. Okay, so I didn't go through it very much, but this thing was sitting on a wheel, and we're depositing material, and we rotate that wheel, so we're putting a line of material on there. Very similar to what you would do with wire arc additive, except then you would have a plate that you were moving. For whatever reason, we designed it as a wheel. I don't remember why we did that. It doesn't matter. But this is what that looks like. So here's the wheel, and here's the wire schematically, and here's the deposit. As the wheel rotates this way, solid material is deposited onto this surface. We did do some imaging. This is what the wire looks like in image. And here's the deposit. You can see this misty area here. That's because, again, our image took 1/10 of a second to collect. So we're imaging over several droplets going across this. So the droplets just look like mist. And here you can see the contact angle of the liquid on the solid substrate. And this is what our beam size looked like relative to all these things. This is relatively to scale. So what we did is we sat the beam here and collected data while material flowed past it, right? So this is, to borrow a term from fluid dynamics, we measured this in a Eulerian reference frame. So we watched particles as they flow by here. That essentially gives us infinite time resolution, right? We can sit here and count all we want because, well, once it's reached steady state. So we can now look at this with much better time resolution. And as you move from x equals 0 here, this is essentially moving back in time, right? As I move my X-ray beam, well, in reality, I'm moving the entire welder. It's easier to talk like you're moving the X-ray beam. As I move the X-ray beam away from the weld pool, I'm essentially going back in time or to cooler material. Okay, so I can do a transformation from where I measure to what time I measured at relative to solidification. So this is a movie of what some of that data looks like, and here's a schematic. This is where the beam is for each of these images. So you can see there's the nice rings that come with diffraction. We actually move forward, and then we go through, there's the liquid. So now, because we're doing it much slower, we go through the liquid, and then it solidifies. You can see the crystallographic texture. You see the fourfold symmetry in this peak intensity. As you go around, that is the FCC 200 peak. So you see the texture is not actually symmetric. It's tilted towards the cold side of the deposit, which isn't too surprising, although we didn't expect it. That's what the raw data looks like. So we make one of these and we cut it, and that's what the microstructure looks like when it's all said and done. This is what you'd expect for AM, very close to the substrate. You get very small grains because the solidification rate is high down here. And as you go up, they turn into columnar grains. This is, for the data I'm going to show you, this is where the X-ray beam penetrates. So we're integrating all of the diffraction from this part of the microstructure. This is what a series of diffraction patterns looks like if you unroll them. So here's liquid material, and this is right after it solidifies, less than a millimeter away from the melt pool. And you can see the texture already in there. Here's that fourfold symmetry that I told you about earlier in the austenitic 200 peak. And it's hard to tell here, but that develops a little bit with time. But one of the first things you catch is that the texture really happens right away. It's formed right away in the process when it solidifies. You can watch the phase evolve. So these are the same positions here, just integrated now over eta. This is the liquid, and I've transferred the liquid diffraction pattern here in the dashed red line. And you can see as it solidifies, these are the ferrite and austenite peaks, the two phases of the steel. But you can see there's still liquid scattering there. So at this point, we're seeing liquid and both solid phases. Now remember, that I haven't really focused on this, but we're integrating through the thickness of this. And this is another issue, is that we're certainly going through a temperature gradient. So if I look at this, you might say, oh, wow, I have liquid and two solid phases all in equilibrium. That may not be true. In reality, I'm sampling from one surface to the inside to the other surface. So there's a gradient there, which dictates part of that mixture as well. But you can watch it evolve. You'll see that the ferrite peak here, the BCC phase of the steel, goes from being the strongest peak to the weaker, and the austenite becomes stronger. So that's the solid-solid phase transformation that you see between those two. And the liquid-solid comes as you see this broad peak disappearing with time. In other words, as you get further away from the melt pool. And again, it's really important that you have all of these diffraction peaks if you're to say something stronger than the alpha peak got smaller, right? And I want to say something stronger than, I want to say the ferrite volume fraction got less, not the alpha peak got smaller. So here's the temperature as a function of time. And again, now we have infinite, because we've set up a quasi-steady state, we have essentially infinite time resolution. So here's the material right at the melt pool. So when we do see solid here, it's again right in the melting temperature range of steel. It cools now because we continue putting heat in it. When we did the point deposition, it was just a quick drop of material and then it cooled very quickly. Here we keep dumping in heat because we're depositing along this line. So that slows the process down. It went from being 1,000 C per second to about 200 C per second in terms of dt. That's what this slope would be. So it cools at that rate, and then at this point we turn the welder off, and of course the cooling accelerates now because I'm not putting any more heat in. We did two different, LD means line depositions, with a little bit different rotation speed. You get a very small difference in the thermal gradient. And something I'm not going to talk about, but we did do models of this, and they actually predicted it quite accurately. So we can pull out the temperature as a function of either distance or time, depending on how you want to look at it. We can pull out the liquid and solid volume fraction, and even now, we don't get very much of the changeover from liquid to solid. That really happens quickly. Excuse me. We do get the evolution at later time, and we actually do quite well looking at the austenite fraction. So the red line here is showing the solid-solid phase transformation as it goes from being, it should form as ferrite and then transform to austenite, and that's what this red line is showing. We can pull out the austenite fraction as a function of temperature now, so we can look at the rate of the transformation. So again, when it solidifies out here at high temperature, it's almost all ferrite, so there's essentially zero austenite, and then as it cools, you see the austenite starts to dominate, and it'll stop at about 95%. So these are the line depositions. Well, those are all the line depositions at different heights above the substrate. If I take that back to the point depositions that we did, you see that it all agrees very well, but remember the point deposition, we had very poor time resolution. We only got 1 point on each of those while it was cooling, so it wasn't so satisfactory. So, and this can be fit, that equation just empirically made up an equation that fits that quite well. I have no theoretical basis for that equation. We can watch the stress develop now. So this is again looking at the lattice parameter as a function of angle. Now I've subtracted off the average lattice parameter so it shows up more, but you see how the strain, if you will, is angle dependent. That's the mechanical stress evolving. What you can really get, because I don't have any reference layout I don't have any reference lattice parameter as a function of temperature. So I can't get an absolute strain. What I can do, though, is subtract the two strains in the opposite direction, because if you subtract, then the reference subtracts out. And that's that difference here. So what this black line is the difference between the strain in the normal to the surface direction and the transverse to the surface direction.
What is distance from wire?
That's how far you are from the melt pool.
Okay.
Right? So as I move the X-ray beam away from the hot spot. Now it turns out I can't get a stress, again, for the reasons I just said, and because I don't have any good assumption on what the stress should be out of plane. I can't measure a stress, I can't determine a stress in any given direction. But it turns out if you look at the von Mises stress, which is actually what drives plasticity in a metal, the von Mises stress is all a function of difference terms. It's usually written in terms of stress, but you can equally well write it in terms of strain. And with just a few assumptions that are very plausible, you can actually get a reasonable approximation of the von Mises stress just from this quantity, the transverse strain minus the longitudinal strain. And you can plot out here now what that stress looks like. That's the red data here is what I would calculate the von Mises stress to be. The blue data is what the temperature is doing. These two black lines are bounding depending on the details of how you make the steel. This would be the upper bound for the yield point of the steel as a function of temperature, and this would be the lower bound. Well, the von Mises stress, again, this is the yield criterion. So when the material reaches this stress, it should yield. So the fact that it follows in between these bounds quite well says that I'm doing at least a plausible job of calculating a stress that's actually meaningful to the prediction of what's happening in the microstructure. I'm actually able to see when the material reaches its yield point and the stress saturates, and it can't go up any higher because now it's flowing plastically. So that now I've spent most of my time on the X-ray measurements. I do want to say some about neutron measurements because there are processes that are slower than you don't need a synchrotron to do, right? There is still valuable work for neutrons to do. What I'm looking at here is the different properties of additively manufactured materials. So here's an example of actually, well, it's hard to see here because it's all one color. Let's just focus on this one. So this is 304L steel that's been made by a wrought process in blue, so that's this one, and 4 different additively manufactured processes. You can see the yield strength of this powder bed fusion 304 steel is more than twice what it is in the wrought material. Okay, so we wanted to understand why, right? So what we decided to do was heat them. I didn't want to, yes I did. So we wanted to heat, let me take it back one step. We want to understand why the wrought material has a different flow strength or yield strength than the additively manufactured material. So here's just, again, another way of plotting. Here's the wrought material, here's the AM material. Of course, you expect it's the microstructure, but there are lots of features in the microstructure that are different. First of all, the grain morphology. So if you compare wrought material up here to AM material, you see the grains are very different. And of course, the grain boundaries dictate how dislocations can flow, so that can affect the strength. Another difference is dislocation density. We measure the dislocation density in the AM material, it's actually quite high. You get a lot of plasticity during additive manufacture. In the wrought material, it was non-detect. Okay, so it was below our instrument resolution. So that affects the strength of the material. Minor phases. You get some ferrite in 304L when you additively manufacture it, when you might not expect to. In the wrought material, and here I'm blowing it up, in the wrought material, maybe you have a tiny little bit of ferrite, but in the AM material, you have quite a bit. That could act as a strengthening mechanism. And finally, something that Livermore actually discovered is that you get chemical segregation. Maybe they didn't discover it, maybe that was too strong of a word, but you get chemical segregation in the material. Again, because it's cooling so fast, the elements don't have time to get to their equilibrium positions. Here it's seen in terms of high areas of chromium. And these are almost certainly the ferrite areas, because if you have extra chromium, then that stabilizes the ferrite. So any of these 4 things could result in that strengthening. So we devised a set of experiments where we heat treated the material in situ. So an industrial process, right? We heat treat it, we anneal it, and we're going to watch each of these things change in the microstructure. And then we're going to test the material again and try to relate which part of the microstructure we pull out to the amount of strength that remains in the material. So we took 6 samples out of 1 block of additively manufactured material. Now I'm going to gloss over this, but we're going to assume all 6 of these samples are the same. We all know when you AM, things change as a function of height. We're going to ignore that. Bear with me if you want. We can talk about it over distilled beverages later. And we went through a bunch of different heat treat processes. Here's the thermal profile that we did. These are this is an hour here, right? So that's 2 hours. So, and we collected neutron data while we're doing all this. So in the case of, for example, sample E, we heated up to 1048 K, so that's 800 C, which might be a reasonable heat treat temperature for steel. Held it there for about an hour and a half, and then cooled it. And we monitored the microstructure while this was happening, so we could see what parts of that additively manufactured microstructure came out during that heat treatment. And then we tested it again to see how that affected the strength. So for instance, you can see as a function of heat treatment temperature, how the peak breadth decreases. So the gray is as built, you see it's a very broad peak, and the higher the heat treatment temperature, you see the peak gets narrower. That's a pretty clear signature. Well, again, if you want more details, let's talk later, but I'm going to argue that that's just dislocation density. I told you in the beginning of the talk, don't believe anything about peak width. Now I'm going to ask you to believe me. You can see here's just a plot of how that full width at half max changes with sample, but in actuality temperature. So we can pull out things like, here's the dislocation density as a function of increasing temperature. That drops off relatively quickly, sooner than we would have expected. Here at about 750 C, the dislocation density has already dropped significantly. It continues to drop with further temperature increase. The ferrite is more persistent. So the red is plotting the ferrite fraction. It persists pretty unchanged up to about 1,000 Kelvin, or what is that, 800 or 700 and something C. Sorry, I can't do that math on the fly. But you see what this gives you. This gives you a recipe if you want to pull out one part of the microstructure but leave another one. This gives you the recipe to do that, which is really what we're all about. How do we do informed heat treatments? Some of the things that we can't see in neutron diffraction or X-ray, well, parts of X-ray diffraction can see grain structure, but in powder diffraction, you can't see how the grain morphology changes. So this is after the heat treatment. We do EBSD, and you can see that after the highest heat treatment, you get complete recrystallization of the grains. Until then, here is kind of arguable, but there's not a huge change of the grain structure until heat treatments in excess of 1,000 degrees C. And finally, the chemistry, you see the chromium dissolves at up here, again, above 1100 C. Okay, so here we have chrome segregated in the as-built material. Here it's starting to dissolve a little bit. By this one at 1,000 C, the chrome is completely dissolved. So you see now we've looked at where all 4 of those parts of the microstructure go away, and I can summarize that in a table. So these are the different samples, the heat treat conditions in terms of time and temperature, the dislocation density, how it's changing, what the ferrite's doing, and then recrystallization. So we made this battery of samples, and then we go back and test them and can relate them to the flow strength. So the orange is the raw material. That's just sort of there for comparison. But you start up in the gray is the as-built, and my laser pointer is getting very slow. In the as-built material, and each heat treatment step reduces that flow strength. So the natural thing to do then is make what's called a Taylor plot, which plots the yield strength versus the square root of the dislocation density. And according to the Taylor law, which is older than most of the people in this room, if not all, that should be a linear relationship, right? And first I'm just showing you, this is as-built material versus material that's been deformed. This was, I can't see the number, I think 11% in compression and 32% in tension. And you can see that nice linear behavior as the dislocation density goes up from deformation. The reason I show that is if you're just deforming it, you can be pretty confident that the only addition to the peak width is dislocations. If you're deforming it, you're not changing chemistry. So the fact that you get a nice line there gives you some confidence. And I went the wrong way. And this is the same line as the one on the right, just on a different scale. But if you extend that same line down to all the heat-treated samples, you see how they continue to fall on that line as the dislocation density drops. and then sample C is the one that recrystallized. So the conclusion that you would draw from this is that most of the strength of the material, which is what you're plotting on the y-axis, is due to the elevated dislocation density. If I take those dislocations away, the material loses strength. When I take the ferrite away, which is sample A, that doesn't change the strength at all. So that tells me the ferrite wasn't playing any role in the strengthening of the AM material. Finally, if I recrystallize it, if I change the shape, the morphology of the grains, that does take away a significant portion of the strength. So for those four things in the microstructure that I identified, the two that control, that give the additively manufactured material extra strength are the dislocation density and the ferrite fraction. I'm sorry, the grain morphology. Forget that ferrite fraction word. Okay, at that point, I'm tired, I'm a little sweaty, and we're out of time. So let me wrap up. What I hope I've been able to show you is that neutrons and X-rays, both of them are very effective at monitoring microstructure, but you have to be careful. You have to understand your assumptions. You have to know how to separate and deconvolute all the different microstructural features that might affect a given diffraction pattern in a given way. Whether you choose to use X-rays or neutrons is very much set by the time scale you want to measure and the length scale of what you want to measure. If you want to measure something big, use neutrons. If you want to measure something fast, use X-rays. But by all means, use the right tool. Even if you have an X-ray machine in your own laboratory, when neutrons are the right tool, use the right tool, and vice versa. We've used X-rays in order to monitor microstructure as it forms from solidification, as we're depositing material in a actual additive manufacture process, if it's somewhat sterilized additive manufacture process. And we've used neutron diffraction to do the same thing, watch the microstructure evolve during a slower industrial process, that is heat treating of the additively manufactured material. And there's some specific conclusions on there, but the whole point of this work, again, and this gets back to what my team's job is we're intending to enable intelligent design of both the deposition process and the post-build processing to achieve desired parameters, and also then to be able to predict what those properties would be. If I can measure a microstructure, I'd like to be able to predict what the resultant properties are going to be, and that's what our real aim is. And at that point, I'll stop and take any questions if you have them.
So, thanks a lot for the talk.
You're welcome.
We have first questions in the audience. Yes, please, Sandra.
Thanks for the presentation. We are very much in this discussion of the convoluting, the different. And I have a question regarding the chemical segregation, because we are also trying to figure that out with respect to the build height, because we observe not only these different phase partitioning and metastable phases, but also for the same phase, different chemistry along the build height. So I don't know if you have a.
Are you talking about titanium? I would guess.
One of them.
So we did the first additive manufacture measurement we did with Livermore in about 2013. We worried about that. It was on a stainless steel part, and we took out D zeros along the whole length. Saw no effect. And that gets back to my statement that nickel, chromium, and iron have almost the same metallic radius. So you wouldn't see an effect there, even if the chemistry did change. In Ti-6-4, and I had really hoped to show Ti-6-4, but I just had too much data to show, it's absolutely effect. When you, especially when you do powder bed fusion, and you know this as well as I do, you get the alpha prime microstructure, you get supersaturated vanadium in the hexagonal phase where the vanadium doesn't want to be. As you go up and the cooling rate slows down, then you're going to get some more segregation of that vanadium. That's going to change the lattice parameter, absolutely. The metallic radius of vanadium is different from that of titanium. So you're much more sensitive to it in Ti-6-4. You can absolutely use, the lattice parameter, particularly of the beta phase, as a way to determine the vanadium concentration. Because you start out with pure alpha and all the vanadium stuck in, when I say alpha, I mean hexagonal. I'm not a metallurgist, I don't use alpha prime. Your pure hexagonal and all your vanadium stuck in there. If you heat it up and the vanadium starts to flow into the beta, that really changes, the beta is really sensitive to the amount of vanadium in that. And you can use the lattice parameter to the beta as a metric to know what the vanadium concentration is in the beta phase.
But meaning for this in-situ D0,
yes,
that we've been discussing this
So that's, we collected in-situ data, just like the steel that I showed you, depositing titanium. And the reason I don't ever show that data to anybody is because I can't figure out how to interpret it. So I have great data of what the titanium, in fact, my student did publish it. I wasn't a big fan of him publishing it. So we can show the lattice parameter, the 110 peak, the 002 peak, changing with time, but I can't separate where the vanadium is from the temperature. They're very similar size effects. They're both scalars. And this is where we tried our one time to try to go really fast. We used the APS calls it an ASI detector. It's a tiny little detector about this big. It ran at 200 hertz. We could see one spot from titanium, from the beta phase, not an entire ring. So you can't get any of the eta dependence of the peak. So we couldn't separate anything. The reason we published it is because there was an interesting thing. You can see the beta change to alpha, and you can actually see the D space. You can kind of see epitaxial is not the right word. I guess the orientation relationship, the 110 of the beta and the 002 of the alpha form with the same lattice parameter within a factor of root 2 or whatever it is, right? Root 3, there's a factor there, but they form the same. And then with a little bit of time, they separate. So there's some sort of constraint of the alpha as it forms from the beta. And you can see that change. So that was why we did publish it. But you can't get anything absolute out of it because there's too many things going on. So I don't have an answer for you, Sandra.
No, but
you look like you're happy because I'm not any smarter than you are.
No, I'm happy because we are struggling with the same because we got this similar offset also with some Inconel, so we can discuss.
Inconel's worse, right? Because the niobium is really sluggish.
Yeah.
So and then it gets really bad because if you heat treat it, now you have local areas that are a completely different alloy, so you get completely the wrong phase, and your turbine blade falls apart. So Inconel is worse than Ti-64. But Los Alamos doesn't care about Inconel, so I'm not allowed to study it.
So the online audience is also welcome to either raise their hand or ask questions in the Q&A. And meantime, Andreas has a question.
Thank you very much. It was a pleasure to listen to your talk.
Thank you.
The process you described, is this additive manufacturing or continuous casting?
So it depends on the audience I'm talking to. So Los Alamos, I mentioned our mission. Los Alamos's mission is to make sure the components that we care about work. The last thing we want to do is introduce materials with different properties, even if they're better. We don't want better, we want the same. So the chance that we're going to start making a component with additive is next to none because we know it's going to be different. So when I talk to Los Alamos, we know we're going to use casting into the future. So I would call this casting. If I talk to the right person, I would call it welding. When I'm talking to you guys, I'm going to talk. Sure. So we're actually our next step, and we'll have beam time in November with a faster detector, the Pilatus at least, so we'll at least get 200 hertz. There, we're going to actually use the exact same machine, but deposit into a mold to look at casting. So you're absolutely right.
And what is a follow-up question? What would be the generic take-at-home message that, let's say, independent on the material you use and the process? You say that additive manufacturing is faster than casting. Depends on the casting, I would argue, but let's say it's faster process. So what would be the take-at-home message?
Well, so I mean, the reality is my take-home message is a technique message. I'm a physicist at heart, a materials or an instrument scientist. I do materials because that's what I'm paid to do. It allowed me to be an instrument scientist. So I don't know that I would give a take-home message about additive or casting. I would give a message about scattering.
No, but if the cooling rate is fast, so
yes.
You say we have a fast cooling rate, we have a large temperature rate.
Yes.
What will influence the property you get at the end the most?
Well, so probably the post-build heat treatment is probably the most important thing. But again, I'm not a material scientist, and you shouldn't take my word for that.
Thank you.
Chuck?
Yes, I have two questions. First one is, I asked myself about the reversibility of the correlation between the microstructure and the strain stress properties. Can you address that by cycling of temperature and continuously follow the evolution of the reversibility?
So I'm not exactly sure I understood the question, but what we did in these, and this is again something that's never quite made publication. So we watched this material as we deposit it, which I showed. But then when it was all done in cold, we went back and mapped it in great detail ex-situ. So then we could get the full 3D parameters and we get better quality data, and then try to relate that to, make sure it's consistent with what we saw form real time as it was forming. I'm not sure if that answered your question or not.
I'm just wondering if you can make cycle of temperature, for example, to see whether the evolution of the.
So we put multiple lines down, yes.
Yeah.
Yep. Okay. In fact, that is in the paper, but I didn't have time. We put as many as 3 lines on top of each other, and at that point we couldn't stack it up any higher. It was becoming unstable. But we did measurements where we'd measure it, and we go back ex situ and map it, and then put another one on top of it, and then go back and map it, and then put a third one on top of it, all in situ, and map it. We tried some in situ heat treating. When we went there, the intent was to have both the wire arc feed, but we also had a laser built onto it. But the control of linking the feed of the wire to the laser so that we could do wire melting wasn't ready when we had our beam time. So what we could do was lay down a bead with a wire and then go over it with a laser and remelt it. So we did do that as well. So we looked at a couple sort of post-build treatment type things.
Okay. So I have another question. Can you identify some local gradient effect at the surface of the grain that tells you that you in terms of volume fraction that they can change the volume fraction as effective volume fraction? I don't see.
So we couldn't do that. So what we do is inherently pattern diffraction. So we wouldn't look within a grain, right? We would not be looking at change of volume fraction, say from the center of a grain to an edge of a grain. When we do the mapping, we can certainly see the ferrite fraction, for instance, as a function of height within the deposit, right? So we can look at that wire and say there's a lot of ferrite on the top surface. And then when we put the second layer on it, we can see that ferrite disappears, but then there'd be ferrite on the top of the second surface. So we can see heterogeneities on a line-by-line basis, but certainly not on a grain-by-grain basis. These measurements weren't done with that. I am 90% a powder diffraction person and 10% trying to do grain mapping type stuff.
I had a technical question. You showed that you can make cuts at different heights.
Mm-hmm.
And before, for the point contact, you had this 0.1, 0.4, 0.8. That is also height?
Yes.
Okay.
Yes. Sorry, I didn't explain that better.
And so one thought that somehow it's you have more strain at the extremes and less in the middle. No?
I'd have to go back and look.
Yeah. Okay. This is some easy way to understand this?
I'd have to go back and look.
Okay.
I don't remember.
Okay.
No, so no, there's not an easy way to explain.
More questions in the audience? In the online audience? No? Then we thank you.
Thank you.
We continue with offline discussions.